Okay, chapter 10, order of group elements. And well, this is a little bit, well, there is a little bit of notation, but there's also about, funnily enough, this is again the modulo thing, right? Another thing that relates to modulo operation.
Well, you can't escape that.
Okay, so we have exponential notation if the operation of the group is expressed with multiplication, and we can notate it with this. So the exponent becomes how many times you are applying the operation. And we can also say that for the negative is when you're applying the inverses that many times. And if you go to zero, you're actually doing the identity element and things. Then pretty much all the properties of exponents hold. Of course, you should prove that, but oh well. We need to check the other cases where each of the integers m and n is allowed to be zero or negative, and that's essentially the proof of exercise A, which we're probably going to skip because we rather do the other exercises. Then there is this division thing, which there is a special name for this division, isn't it?
It's Euclidean division, yeah.
Yeah.
Oh,
Which,
hello, Ace.
hello Ace.
No.
Um, which well, I usually don't think in those terms, but that's on me. But it does make sense, right? So if you actually make the remainder always non-negative unless dividend, this is how this division works. It's not like the positive division and then just slapping a negative on it. You have to think in these terms here. Um, the important principle is called the division algorithm, and you can express generically like this, right? So m is equal to n times q plus an r, where r is always greater than 0 and less than n. At this stage, we will take the division algorithm to be a postulate of the system of the integers. And then we have our first thing. If there is a non-zero integer m such that a to the power of m equals to e, then there exists a positive integer n such that um, a to the power of n equals to e. And why? Because if m is negative, then we can say that a to the power of minus m can be expressed like this, but we know that a to the power of m is equal to e, and the inverse of identity is identity. Thus, this is equal to e, where minus m is positive. This simple observation is crucial for our next definition. Let G be an arbitrary group. Okay, so the important part of this portion is that because you know that there is a non-zero integer, that this is true, you can always say that there is a positive one, that this equality is also true, and the reason that is because the inverse of the identity is identity. Then you say that if there exists a non-zero integer m such that this is a typo, right? Because it's a to the power of m equals e. Then the order of the element a is defined to be the least positive integer n such that, yeah, and the least positive thing is going to relate to modulo in a bit. If that's not true, if there is no non-zero integer m, then we say that the order is infinity. Thus, in any group G, every element has an order which is either a positive integer or infinity. If the order of A is a positive integer, we say that A has finite order. Otherwise, A has infinite order. I don't know if this is related to any of these things, but I kind of got reminded of cardinality by reading this thing. Again, I don't know if it relates or not, but that's what I thought of it.
Uh, I don't think it does, or if it does, it's only tangentially.
For example, let us glance at S3. Then we say that it's customary to use exponentiation. We've seen this before many times. The order of alpha is true because if you apply alpha twice, you get identity. And 2 is the smallest positive integer which satisfies the equation. The order of beta
Well,
is
wait. I
3.
think I think that's eta though, which I think isn't that the not the identity element, but the smallest element, right?
You say this?
Yeah,
No,
because that's not the identity. I could be wrong. I could be
the,
misreading.
I think this is definitely identity, but we can go to the page. So 72. The problem is that this PDF doesn't have any pages, so how the heck I'm going to discover 72? Here's the hack. Have the physical book.
Yeah.
72.
I think eta is used as the identity when you're dealing with
Permutations, right?
functions.
Or functions.
Oh, okay. Sorry, it's been so long since I read through this book, so I don't know
That's fine.
the notation.
Yeah, it's definitely
And of
identity.
course, and of course, I've missed every meeting.
Well, to be fair, it seems that you like to hang out on Sunday, so that's fine. We are
Yeah,
only doing this
weekdays are not
today.
the
Okay,
best
let
days
me
for
actually
me.
give you the context. We are doing this today because I have a vacation on the next week on Thursday, which means I won't be available on Sunday, and that's why we are like bringing it to
Fair
Tuesday.
enough.
Okay. Anyway, oh, actually, I forgot to check that. Alpha square is equal to identity. Is that true? Yes. Okay. So the order of beta is 3 because if you apply beta 3 times, you're gonna get the identity thing. Yeah, this is probably the context of the functions that Marinho mentioned. And 3 is the least positive power of beta equal to identity. Is clear similarly that gamma has order 2, sigma 3, and this one I don't know, but it has order 2,
Kappa.
kappa. It is important to know that one speaks of powers of A only when the group's operation is called multiplication, because if it's addition, the notation, we speak of multiplies of A instead of powers of A, because, well, their parallels are clear, I suppose. And why the negative multiplies of A are that, and then that. And then in Z6, which is modulo 6, right, on integers, the number 2 has order 3 because if you use the operation addition 3 times on 2, you get the identity element. Which again, in my eyes, this order stuff is all about converting everything to modulo. Everything is now isomorphic to modulo. And no smaller multiple of 2 is equal to 0. Similarly, the order of 3 is 2, the order of 4 is 3, and the order of 5 is 6. And that is because if you do the operation in Z6 of 3 twice, you're going to get 0. So that's why the order of 3 is 2. And so on and so forth. In integers, number 2 has infinite order because no non-zero multiple of 2 is equal to 0. As a matter of fact, in integers, every non-zero number has infinite order, obviously. The main fact about the order of elements is given in the next two theorems. Okay, so, and here's the thing. We've seen this before. I 100% don't know what was the context, but we're going to talk about multiples of something, and then we can collapse, like we can factor out the multiples, and then we keep saying identity equals to identity, and because it multiplies by identity, it just disappears.
I was trying to use the isomorphism to modular arithmetic in some proof we discussed on some chapter past, but I also don't remember the context.
We've seen this a few times actually.
Yeah, it is the same thing, isn't it? Like the fact that being multiple means that you are doing the wraparound, everything like just clicks. Theorem 3. Powers of A, if A has finite order, if the order of A is n, they are exactly n different powers of A. Namely, so these ones. The only problem is that you have to prove that they are different, and we're gonna go there. What the theorem asserts is that every positive or negative power of A is equal to one of the above, and the above are all different from one another. Before going on, remember that the order of A is n. Hence, because this is what we saw before, right? Because if there is a non-zero number m, non-negative and non-zero, then there is a positive one, and we are defining that n to be the smallest positive integer which satisfies this equation. Okay, so let us begin by proving that every power of A is equal to one of the powers, right? So the multiple thing. So let a to the power of m be any power of a. Use the division algorithm, the Euclidean one. So then we know that m can be factored into this. Then we say that, then we exploit, man, this PDF version. So many typos. Anyway, this is basically that, right? Because of the exponentiation property. Then we do it again, and we do that, but we know that this is equal to e. Then it's going to be e to the power of q, which is e, which means that this is going to cancel out, and we have a to the power of r. Thus, this holds, and r is one of the integers, because that. Cool. Now we have to prove that these things, a to the power of all of those, are all different. So we're going to do by the contradiction, right? So suppose not, so suppose that they are the same, where r and s are distinct integers between those two things. So either that or either that, which is true. Thus, we can say that. Well, we're going to pick one, but we can prove the other way around by doing the symmetric version. So consequently, we say that this is true. And this is confusing to me, this manipulation. I don't know if I completely got it, so you guys can correct me. So if we say, okay, so it starts by saying, okay, but we know that these two are equal, right? And R and S are different. And then we immediately jump into this, right? But my understanding is that we are relying on the fact that this is actually a to the power of n first. And then we are using, like, applying the same operation to the both sides of this inequality and just working on that. Is that what you guys understood from this first left-hand side of this first equal here?
Not really.
Okay, so how is this come to be? Why are you doing a to the power of r minus s? Why are we doing that?
Well, we're trying to get there because we want to hit the contradiction, right?
Sure.
And the way to get there is, okay, we are assuming that r equals s, but we know
No,
that
no, you're assuming the opposite. You're assuming that their exponentiations are the same with r and s being different. And then we are gonna try to find that this is that something contradicts something else.
Oh, yes, you are correct. I misspoke. So yeah, you are assuming that those exponentiations are equal, despite the fact that you are using r and s, which are different.
Yeah.
Um, but that means that actually uh, a to the r times the inverse of a to the s should be identity, right?
No, yeah, no, that is the demonstration that is happening here. That still doesn't explain why we're doing why the left-hand side is is this to begin with. That's my question. Why are we starting from this point? The only thing that I could think of is because we are applying exponents to both sides of this inequality. If it's not
Maybe
that,
it,
then I don't understand.
maybe it makes more sense if you start with the right-hand side and then rewrite it to the left-hand side and then follow the proof.
Wait, you said to read from the right to the left?
Yes, you have that the right is clearly identity, right?
Yes.
And if that's clearly identity and those are equal, then it means that you can replace a to the power of s with a to the power of r.
Ah, okay, so
So
you're
you get
reading.
the
Okay, I
left.
see, I see, I see. So you're saying that. Okay, but then this is, again, creativity out of nowhere, right? Because how are you going to know that, oh, actually, I'm going to pick identity and rewrite it in this way because then I can use that and here and that. Sounds out of the blue, especially given that we started from this equation 1 here. But anyway, I think I'm going to go with what Tevo said. So I'm going to read from right to the left, starting with identity, and then I'm going to rewrite it in this because this is equal to a times to the power of s minus s, right? And you can rewrite it in this way, but because we are trying to say that these things are the same, you can swap the left-hand side of so this guy with this guy, and then you can just manipulate from there and get to the conclusion that a to the power of r minus s is equal to e. But this should be impossible, right? Because by equation 1, we know that r minus s is a positive integer less than n, where n, which is the order, is the smallest positive integer such that this is true. So this cannot be, and then we just, hence we proved that they must be different. This proves that we cannot have that where these are different, right? Because we can have those, but if those are the same, right? But that's kind of like, which means that these must all be different. Okay, so theorem 4, powers of A. If A has infinite order, if A has order infinity, then all the powers of A are different. That is, if R and S are distinct integers, then these will never, they will never be equal, right? So let's prove it again. So let's we need to say we're gonna say that they both are integers and suppose that this is true. Then we do the same trick as before. We conclude the same. But A has order infinity, and this means that a to the power of m is not equal to e for any integer m expect 0.
That's a typo.
Where?
Expect should be except.
Except, sorry. And I said it as it was except, but I think that typo is in the printed book as well. That's why I knew. So except. Well, I think it is in the printed version as well, which is a shame again. Okay, so thus, right? So we know that this must be 0. This subtraction here, r minus s, which means that they are the same. Which means that if this is true, this must be true, which means this as well. This chapter concludes with technical property of exponents, which is tremendous importance, blah blah blah. If A is an element of a group, the order of A is the least positive integer n, such that this is true. But there are other integers, such say t, such that this is true. How are they related to n? And I think this is going to also again talk about the multiple things. Suppose an element A in a group has order n, then this a to the power of t equals to e if and only if t is a multiple of n. Then we're going to say that if it is multiple, then we can just rearrange these things, right? And then we can just like abuse the fact that we know that a to the power of n is equal to identity, and then don't matter how many times you try to get out of it, you're always going to get identity. And then conversely, suppose that this is true. Divide t by using the division algorithm, so that. Then you manipulate that a little further, and you're going to get, again, we've seen this before, a to the power of r. Thus, we know that this is true. If r is different than 0, then r is a positive integer less than n, where n is the smallest positive integer such that this is true, which is impossible, right? Because by definition, r cannot be a positive integer smaller than n, that this holds because we know that n is the smallest positive integer that this is true. And this is not written here, but this should be impossible, right? So impossible, hence the r needs to be 0, and therefore we proved again that t is multiple of n. If A is any element of a group, we would denote the order of A by doing that. Cool. So again, more connections of more things to modular operation, which is maybe this is going to be the conclusion out of the book, if so far. What have you learned? That modular is cool.
I wish more languages had the proper Euclidean division version of modulo. Because that's surprisingly rare among programming languages.
Well, but here's the thing. You said the Euclidean division version of modulo. That's what you said, right?
Yeah, this one, where the result is always at least
positive.
0.
Yeah, positive, right? What is the reason that's... What would be the reason that this is not common?
Because this is typically not implemented in hardware, and most languages just surface what the hardware gives you.
Well, but that's postponing the question, right? Because then the question becomes why we don't have dedicated hardware for this type of division. To
I have
me,
no idea because actually it's fairly easy to get this operation out of the operation that the hardware provides you with just some minor
that's
manipulation.
not how this industry works. If you're trying to make dedicated hardware, the question is, what is the big problem that having this factory production ready it will become easier to solve it? So I don't know on top of my head which problem is a very big problem that humans want to solve that would justify making this in a factory as hardware. If you know, if you are a fan of this, you may know, Marin. So, which type of problems become easier if you have this handy and fast?
Um, I'm pretty sure cryptography uses modulo a lot, but then there are already dedicated hardware for specific encryption algorithms, so this may not come up in practice actually.
Ah,
Does cryptography not usually deal with unsigned numbers?
I have no idea.
Which means they sidestep this issue entirely because you're only dealing with positives.
That's fair. Like pretty much every implementation of remainder agrees when both arguments are positive. They only diverge when at least one is negative.
Yeah. But again, I think that my understanding of the hardware industry is that you need to have a very good argument to justify mass producing this on hardware level.
So I thought that x86 did have integer divide. It's just really slow and not used.
It has, but it doesn't have. It's not. I'm pretty sure it's not Euclidean division though.
Yeah.
Oh,
Ace,
okay.
it does
I
have
see.
division as like in hardware. Like, I know
Yeah,
that. That is true. But this is a
I
different type of
misunderstood.
division. Yeah, this is the division where the remainder is always positive.
Yeah, I'm pretty sure x86 gives you truncating division, which is not quite the same.
Yeah, it's definitely not the same. Well, they converge if the things are all positive, as Steve said, but if you have a negative in the middle of the way, then it's completely different, right? And again, I'm not saying it there is no problem that uses this to solve it better. I'm just saying that if we have like 70 years or whatever of making hardware for computers and this is still not there, then it probably means that there is a very few problems that can actually be sped up by having this implemented in hardware. That would be my guess. It would not be the first time the industry is being done. So I would believe you if like no. This is just a skill
I'm
issue.
pretty. I'm pretty sure the industry is being dumped because like we already have division in hardware. It's just not the correct version of division.
No, but that doesn't mean they are dumb, right? Because rearranging and making special units with the rewiring the things that's just still costly, right? So again, you have to have a very good argument for it.
Silly question. If you were to draw out the circuit for it that does the division, would one type of division be simpler to implement in hardware than another type of division?
Simpler,
Maybe. I
Maybe
really don't know.
simpler. That's the question.
like
Um,
take less transistors or something.
Yeah,
I'm
yeah,
gonna
I
answer
would assume.
as go Ace.
I would just assume. I don't know for a fact. But yeah, I mean they're two different algorithms, right?
Yeah, no, but Tevo is asking if you make this one, can you optimize the other one? I don't know. I have no idea.
Like is one simpler to express in terms of AND or
Mhm.
XOR
Yeah,
gates or
yeah, yeah,
whatever?
yeah, yeah. Yeah, we could, in theory, try that out ourselves. Like we can just boot up like whatever open source VHDL exists and just try to do that. But on top of my head, I don't have any intuition to answer your question. Uh, and again, I'm not saying that there isn't any case. Maybe we just don't know because again, It wouldn't be the first time the industry does that. They purposely choose to do that.
Setting the question of hardware aside, it's even sadder that actual languages, like high-level languages, don't give you that because actually Euclidean division is more optimization friendly.
Well, that may be
Be-
true, but again, uh, if you don't know the problem, like, forget the hardware question, right? Let's go to the actual software question of like, where would you use this to solve something? And I remember at least one case when we were implementing physics for Lyceum. I remember that we needed this at least once, right? Specifically this division.
Anytime you have something that needs to wrap around, this is useful.
Yeah. Well, I mean, if you have to wrap around considering the negatives in the mix, right? Because if you have only the positives, you can just use the normal thing.
Well, yes.
Well, but there are cases, and again, I just remember one, which is when in our game, right? In our prototype of the game, I clearly remembering you and Mageta saying, "Wow, it would be very convenient to have Euclidean division here," but we didn't. Or maybe it was on Mahjong, I don't remember, but there was some rotation thing that we kind of wanted to have it. Anyway, okay, so exercises, group A, we have 34 minutes, so that's not going to be enough for sure. But let's try to speed this up. So this is about using the properties of the exponentiation for the order cases, right? Where m or n, they may be zero or they may be negative, or mixing them both. Um,
Yeah, this is basically here are the familiar laws of exponentiation. Try to prove them in the case of an abstract group instead of the numerical context where you're familiar with these already, right?
maybe I'm just dumb, but to prove the like, okay, maybe the word prove is a little strong, but can't you just replace, like, grab these equalities and replace these things in there and see if they hold? Or am I missing something?
For zero, you can. For the negatives, it's a little more involved, but you can just use the argument on the original proof with negatives instead of the normal element.
Oh, you mean extracting the negative, right? The negative portion of the exponentiation. Is that what you mean?
Uh, I think on C you can do that. On B, I found it easier to just express it as a minus one uh, m times, and then extrapolate that, and then follow the rest of the proof like the original one.
Okay. Yeah, but that sounds like doing this, right? Extracting, and like, you have this, but you can just do that, and then you go from there. Is this what you meant?
I meant that on the C case,
Yes.
although I don't have the C case written down.
Yes. Okay, so example of orders of elements. What is the order of 10 in integers modulo 25? Uh, so the order of a number, as we've seen the example, it is how many times you need to apply the operation using the number again until you have the neutral element, right? So this is modulo, so we are reaching for 0.
Yeah,
Um,
basically, how many times do you need to add 10 to get to a multiple of 25, essentially?
isn't that like 5 times?
5. Yeah, it's 5.
Yeah. So this is always like, what's the name of this? It's the minimum, least something, something, common.
Least common multiple,
Yeah,
yeah.
LCM.
It's actually like if you have an
Actually,
m on Zn, it's the least common multiple between m and n divided by m, assuming m is different than 0.
oh yeah, the least common multiple actually only, well, it gives
Yeah,
you,
yeah, it's what Evo said.
yeah, it gives you the highest possible
Yeah,
lower bound
yeah, yeah,
as, and it only holds if they're like, we're gonna see this in later exercise, but it only holds if they are relatively prime. If they are not, then actually the number is even lower than that. But yeah.
Yeah. So what is this one? 8?
I believe it is 8, yes.
Yeah. I've seen the okay. So this is blue, right? So this has the answer, and the answer is hilarious. The answer is 4. Explain why. Damn. Like, and the answer is 4 because of the number 1, right? So if you follow the arrows here, the function f maps f to 6 and 6 to 4, 4 to 2, and 2 back to 1. And that is the least amount of, well, that's the most amount of cycles that you need to repeat yourself. Because in the other cases, 3 is locked in and 5 is locked in. So everything else is about reaching the 1. Or reaching the 2, or reaching the 4, or reaching the 6, doesn't matter, right?
Yeah,
But
depends on
it's
where you
4.
start.
Exactly, but this is 4. But the answer is just like, it is 4. Explain why. What is the order of? Yeah, I actually. Okay, so this is one where, as I said, I didn't have the time to properly think of every single exercise in my head. But so it seems that the answer to both of these questions will be different, right? Because in one of them you don't have the 0, which is this one, and in this other one you don't you have the 0. So in this one it's probably going to be infinity, right?
Well, yes, because if you keep adding 1, and
Yeah.
remember the operation is also different, right? So on the right, if you keep adding 1, you will
Ah,
never
that
get
is
to
the
0.
plot. I keep forgetting that when you remove the 0, the operation also changes.
Yeah, but on the left, 1 is actually the identity element.
So this
So
is
the order
multiplication.
is, yeah, this multiplication. So
I
the
see.
order is 1,
Yeah.
because if you have 1, then you have the identity, so you're done.
Okay. Okay. So does anybody have questions about exercises B?
Not really a question, but I found 6 down there to be pretty interesting to think about.
Can an element of an infinite group have finite order? Well, we just saw, right? This.
Well, yes, but 1 is the identity, right? I was thinking, okay, what about an arbitrary element? One that's
The
not
answer
the
is
identity.
still yes. And
Mm,
a nice example is XOR on the natural numbers, where everything has order 2 except the identity.
yeah. Okay, that's fair enough.
Another interesting example is -1 in the multiplicative group over pick your number system, right? Integers, rationals, whatever.
You said in which number system you said?
In a multiplicative group in whatever number system, right?
Oh, I
So
see.
if you multiply -1 by itself, you get 1, which is the identity. So it has order 2.
Yeah. No, but I said I thought you said another term that I never heard before in the previous way to talk about it. But you said just whatever number system. Okay.
Yeah, it could be the integers, could be the rationals,
Yeah.
any number system that has negatives.
Yeah. Okay, so next up is C, elementary properties of order. So this is also the one that I don't know. Okay, I have questions about this one because 6 is talking about well, 6, 7, they're talking about commutativity, right? So the things can be reversed. I don't know how I want to talk about it because I don't know how to do that. But it starts very easy, right? So if the order of that is equal to if and only if, it's asking us to prove it even though this is very intuitive, right? This is very, very intuitive.
Yeah.
Um, so if A has order n, then a to the power of n minus r is equal to this, right? And the reason is because you can refactor that until you get an a to the power of n in here, and then that's going to become identity, and then this just becomes that. Easy enough. That was actually one of
Yeah.
the easiest ones. Okay, so let's prove. Okay, actually, let's do 3, and then let's jump to 6. So if this is true, where k is odd, then the order of a is odd as well.
Yeah, this is
Uh,
a pretty interesting one. And it has to do with um, number theory, specifically about parity under multiplication, right? Because if you have an even number, then whatever you multiply it with, the result will also be even because it will have a factor of 2 from the even number you are multiplying with.
yeah. Okay, actually, before you continue, Marinho, why is this not trivial? I think that's pretty important because we don't know that we don't know if k is the order of a, right? Because in the just by like intuitively, you're trying to say that the order of a is k, but we don't know that, right? We don't know that, but
Well,
we
we
do
know
know.
that
Go on.
it's either k or a multiple of k, and
Yeah, no,
then
but
from
no,
that
but
we
that's
can.
what Marinho is talking about. The second case where you say that k may not be it, but it may be a multiple of what it is, then the odd thing starts to become clear, right?
Yes.
So I just want to clarify that because in the beginning I was like, wait a moment, isn't this obvious? Oh no, but I was assuming that k is the order, and that's not written there. Okay, cool. So 6. The order of VB is the same as the order of BA. So how are you going to do that if we don't know if this is an abelian group? So how do you plan on doing that? So one of the things that I thought is that you can exploit that if you have BA to the power of n, there will be ABs in here, right? There will be ABs in here, and maybe you can do something with that. But I haven't gone that route. So what should you guys do?
Isn't it because multiplication is associative?
Well, it is
I mean, I guess that
associative.
just literally,
No, no,
yeah,
no.
I guess
No,
that's
but
just
this is
literally
not
restating
associative.
6.
Yeah, but this is not associativity, Ace. This is commutativity.
Oh, commutativity. My
Yeah,
mistake. Yeah.
we know that they are associative because G is a group, but it's not saying
Right.
it's an abelian group. That's the
Right.
catch,
Right. Right. Right.
which means that you cannot just do that. But again, my hypothesis is that because you are replicating BA multiple times, you are forming ABs in the middle of it, and maybe that is where we will go somewhere. But Marin will probably know the answer to that. So Marin,
Honestly, I didn't spend much time thinking about this one in particular. Um, Let me think for a second. Yeah, you can probably do something with the ABs, but then you'll be left with a BA at the end if you do that, right? So I'm not sure if that actually helps.
well, I was assuming that would help us because we're gonna have a BA at the end, but we know the order of everything else. Like we can collapse everything else, right? And then just say like and do something with that or something. It's also saying that if this is true, this is a hint, right? If this is true, well, it is assuming that BA to the power of n is equal to e. Then a is the inverse of x, right? Because it's saying the x goes from this b all the way to this other b. And then this is true, right? Because we know because this is a group and there is an e on the other side and we have an a here, then this entire thing must be equal to the inverse of a. Which also means that a is the inverse of x because that's what we were naming this thing.
Okay. Well, maybe let's simplify it to just BA. So then, how do we prove that BAB?
I think I see actually. It's because this is exploiting the fact that even though the group may not be a billion, um, an element and its inverse always commute.
Ah, okay, that is true, right? That is one of the theorems from like way back in the day. Uh, so you can just say this, right? And well, but again, we still have to go one step further because we have to prove that the order is the same.
You can use that to flip the elements and transform one into the other, essentially.
Ah, okay, that is very interesting. And I guess you're gonna also do the same kind of thing in here because again, somehow, like this is very weird because we can say shit about the other permutations of ABC even though this is not an abelian group.
Uh, oh, actually, not even permutations. Those are specifically rotations. Like the order is the same, it's just wrapping around.
Yes, the order is the same, it's just wrapping around. Uh, let blah 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 be the product of some factors permuted cyclically, then the order is the same. I think this is just a generalization of this, right? And I guess
Yeah.
you're gonna get the principle of this by doing this one.
Yeah.
Fair enough. Okay, so exercise D. We still have 20 minutes to go. Okay, so this is starting to talk about prime numbers, the freaking prime numbers, right? So if we know that a to the power of p is equal to e, where p is a prime, then a has order p. Again, how can we say that? Oh, of course, it needs to be right because if p, well, this is p. If p is a prime, that means that there isn't any other guys below him to make this equality hold. Then A must have the order of P. And
Uh,
we know that this, and because this is true, P cannot be 1. Yes, Marinho?
you can probably do something with the fact that 2 is the only even prime to prove
Really?
this.
No, but
Yeah,
again,
because remember, we
go on.
just saw that, like, if you know that a to the k with k being odd holds, then the order has to be odd, right?
Yeah, but I don't even think you need to go that far because here's the thing: if P is a prime, what does that even mean? That means that it's only divisible by P or by himself, by itself, or by 1. But we know that this is true, which means that P cannot be 1. But if P is a prime and it's not 1, it cannot be any other number below it. Which means that P must be the smallest positive integer that this is true, which means that P is the order of A. Like, am I missing something?
Mm, well, I guess that works because, like, yeah, because, like, you know that if a to the p is identity, then any
And you know P
multiple
is
of
not
that,
1.
and you know p is not 1, yes. Um, well, 1 is not a prime, so it cannot be 1.
No, yeah, but then you wouldn't be able to say what I. Um, well, I guess that's true, right? Because you can also say that. Then this is not necessary. You're right. Uh, anyway, I think this is pretty straightforward. You just have to say like something similar to what I said, and you're going to conclude that P must be the order of A. The order of A to the power of K is a divisor factor of the order of A. Well, that's you just use a theorem, right? You just use which one? This one. You just use theorem 5 in the proof, and there you go. If the order of A is equal to Km, then the order of A to the power of K is equal to M. Again, you're probably going to do something with theorem 5 because you're going to factor the multiples. This is all about multiples, really. And then there's again the odd thing, right? So it's saying that if the order of A is equal to n, where n is odd, then the order of A square is equal to n. A square is equal to n. Yeah, actually, wait. This is not clear to me. What is the relationship between this square and being odd? Do you see, Marinho?
I think it's similar to what we saw when we were talking about powers of cycles.
If you multiply an odd number by 2, it's not odd anymore, right?
No, it's not really. Well, you're not multiplying an odd number in this case. You're saying, okay, um, the order of A is odd, which means
You
the
have
cycle
n
has,
different n elements, right, in the thing.
yeah, the cycle is odd, right?
Yeah.
So if you do A squared, where you're basically taking 2 steps instead of 1 along the cycle when you try to multiply that as your initial element, 2 is not odd, so it cannot properly, like, you're not going to cut down the length of the cycle because you're never going to line up with, like, you cannot multiply 2 and get an odd number basically. So you will never, like, they'll never synchronize, I guess is the term I used back then.
I see what you said. I definitely see what you said, but I still don't. I'm not like there's still something in my head saying, but how can you know then that the cycle is gonna be as the original, but again, that's weird. But well, anyway. If A has another n, and we know that these two things are the same, then n is a factor of the subtraction. Well, I guess this must be yes, right? Because if A has n order, you just have to manipulate this thing. So you have identity on one of the sides, and you're gonna see that this subtraction will appear for sure, or something like that, and then it's gonna be A to the power of n, but n written as in these terms. I think that makes sense to me. Okay, any other interesting exercises on D? Have 14 minutes.
Not really.
Okay, cool. So E, relationship between order of AB, order of A, and order of B. Yeah, so this is again. Yeah, actually, I want to do this first one because I couldn't see a relationship between least common multiple and the fact that they commute. But anyway, so let A and B be elements of a group G. We know that the order of A is M, and we know the order of B is N. And we know we're going to use this to denote the least common multiple between M and N. So that. So here's the first thing. So if A and B commute, then the order of AB is a divisor of that. Yeah, I have so many questions. What is the relationship between them commuting and the divisor of that? Least common multiple. And then there is the exercise 6, right? To give an example to show that part 1 is not true if A and B do not commute. So if A and B do not commute, then it's not a divisor between those two, the order of AB.
Hmm.
Okay, so the first question that I have is, what does it mean to say the order of AB? So we are getting the product, like the literal product of AB, and then trying to get the order of that in the group? Is that what
Yeah,
we're doing?
that's exactly what we're doing.
Okay, so why does it happen that when you commute, you can just say it is the... Actually, the opposite question is more interesting to me. Why, if they don't commute, then there is no divisor of LCM?
Hmm.
Like, I'm having a hard time understanding why commuting matters. Because if you're going to multiply them anyway, that's why I asked the first question, if this is a literal multiplication.
It is, but I think this might be related with the fact that an element and its inverse always commute, even if the group is not abelian, right? So if A and B commute, then maybe they are made up of inverses of each other in some sense.
Ah. Yeah, but then why does that matter? Again, if you're going to multiply them anyway, what does it matter the order that they come from? Or that they are placed?
It matters because if you can commute them, you may be able to cancel out and get an identity earlier than if you cannot.
Ah. And then the minimum amount of hops that you need is going to be the divisor of this?
A divisor of this.
A
Um,
divisor. Interesting. So you're saying that if they commute, then you can create identities between the process before actually going through the entire chain. And then you can just say that this is simplifying the amount of chains until you end up with a divisor of the least common multiple.
Yeah, this is the route I would go down to actually prove this. I haven't done this because honestly, this is actually one part of number theory that I don't usually think too much about. I'm more interested on the GCD side of things because of rational numbers.
Yeah. Yeah, but I think that satisfies me, even though we didn't prove it, right? For in any sense, we didn't prove it. We just have an idea. So your idea is exploiting the fact that if they commute, they must be inverses to each other in some sense, which means that you can rearrange them in a way that you can simplify them before doing the hops. And then when you finally simplify enough of them, wait a moment, that means that you're always going to end up with a couple of A's or a couple of B's. Because if you have both, you can always commute it again and get them, like remove them.
I mean, it kind of depends on their internal structure, I guess, which we are not given, right? We just know that they commute. So,
Well, I'm assuming that there are only A's and B's.
well, there may be other elements other
Well,
than
there
A
may
and B.
be, but to that idea to work, to me, you have to have like you have to be able to always commute if they commute. And if you have a G in the middle of the process, then everything is fucked. All right?
Or even a string of just A's or just B's, right?
Yeah, but if you have that ace, that's the thing. If you have a string of those, you can rearrange them because they commute. And what Marinho is saying is that if they commute, then they, well, his intuition is that they
Oh yeah, yeah, because they commute on the edges, right? Okay, and you could
exactly.
just
And
shuffle them
then
in.
what Marinho is assuming is that if they commute, they may have an inverse relationship to each other, which means that you can collapse them with an identity every time you make a pair.
Well, not necessarily a direct. They may not necessarily be direct inverses of each other, but like maybe some powers
You
of the
can
maybe some power of
fact
A is an inverse of B. I don't know.
you can factor them out in a way that you can get the inverses of each other, I guess.
Exactly, which is what Marinho just
Yeah.
said. But then here's the thing. After you do that, assuming you do that, in my understanding, no, what you guys said just disproved what I said. Because I was about to say that you're going to end up with a bunch of A's or a bunch of B's. But if they are working on the way that you guys just said, if it's a power of something, then you may have A's and B's at the final product, right? Then again, we are also saying that's going to end up the amount of hops to the thing. It's going to be a divisor of this. Yeah, it's not 100% clear, but I'm very satisfied.
Yeah, but
The,
but why is it a divisor of that least common multiple?
well,
What is that process? That's I
my
think the tricky part,
yeah,
right?
yeah, my intuition is because we know that A has an order and B has an order, and we are trying to do the order of the product. And because we know that they commute, we are assuming we can cancel some of them out. How do you know that it's going to remain a divisor of that? Then I don't know.
Oh, because right, because they cancel out, that becomes a
And now again,
divisor.
I don't know how you're going to prove that. How you're going to prove that
Hmm.
after you cancel them out,
Well,
the remaining ones will mandatorily have hops to make this true.
well, in the worst case scenario, let's assume that it's not actually like the divisor is actually itself, right? Because every number divides itself. That's the worst case. Well, in that case, you will have m times n. Actually, not necessarily that, right? But you have something that ends up with. Actually, let me take a step back. If you do m times n, that's definitely
A common
identity, right?
multiple.
Because
Yeah,
a
that's
and
definitely.
b, because that many, you have that many a's and that many b's, so like they will cancel out at that point. In particular, m times n is a multiple of m, so all of the a's cancel out, and it's a multiple of n, so all of the b's also cancel out, so everything cancels out, so it's identity. The question is, okay, given that they commute, can you get um, can you get something smaller than n times n, right? I think that's the direction you have to go
No,
to
no, no.
actually prove this.
That's definitely the direction we were going with the whole cancellation thing by like manipulating the thing. But it's still not clear to me how you're going to do the jump to say that okay, they commute, and then there is a particular relationship between A's and B's that make them inverses of each other. It can be the power to some k or whatever, it doesn't matter. But how do you know that after you cancel all of those, the remaining group of A's and B's there, they will actually, if you like, and then if you do the product on them, how do you know that that needs a divisor of the least common multiple to do the hop, like to do the wraparound? That is the missing piece in my brain. Like, how do you know that?
Yeah, I think I would have to actually sit down and work this out in order to give you an answer, Lemos. I'm sorry.
No, that's fine. We are here just to try an intuition in 1 hour. That's fine. But yeah. And then a very interesting concept is the concept of relatively prime, right? So two integers are said to be relatively prime if they have no common factors except plus 1 and 1. And there is even an example somewhere of like 15 and 8 or something. Anyway, so can we go? We have 3 minutes, guys. We have still 3 exercises to go. So any more comments of E? Gonna go to F. Cool. So F, orders of powers of elements. Right. So let A be an element of order 12 in group G. What does that mean? It means that you have to apply the operation A to itself, with itself, 12 times in order to get the identity element in G. What is the smallest positive K such that 8K equals to E? And the answer is probably 24. No, 3?
Yeah, it's 3 because
Yeah,
24 is the multiple of 12.
yeah. And again, the multiple thing works because, well, we already proved that in the reading, right? So it's because the multiple means wrapping around, being a multiple, because of theorem 5. Uh, what is the order of A times 8?
A to the 8, it's 3, no? Because we just saw that if you... Actually, is it 3? Yeah, it is 3, because we just saw that
Yeah, it is
if
3.
you do a to the 8k with k equals 3, if you just factor that out, you get a to the 8 to the 3.
Yeah, and this is going to be 4, this is going to be 5, and this is going to be 10, right?
Then,
Not 10,
why?
sorry, 12.
Yeah, you basically just have to do the same exercise 1 uh, with those numbers instead of 8, and you'll get them.
Yeah. Okay, so I don't think that this F is much more interesting than that. Like, we have more, of course, you always have more complicated exercise at the end. Um, I don't think they are that much different than these ones that we just did. And again, this is very easy because you can just isomorphically go to modulo and you're done. So let's go to G. All right. So what is this one about? So yeah, we know that again introducing the concept of relatively prime, and and the examples are 15 and 8, right? Because they can be factored out into primes, these two numbers, but they don't have common primes because this one is only 3 and 5, and this one is only 2. So they are relatively primes, which is a very fun concept. I never thought of that in those terms. Here's a useful fact: if m and n are relatively prime, and m is a factor of n times k, then m is a factor of k. So there is no examples in here, but I think it would be educational to do examples.
So actually, I think the missing piece with that divisor, the least common multiple, is probably due to this, like something being either relatively prime or not relatively prime, is my guess.
Well,
Thinking back,
but we don't know the prime nature of those two things. Like I think in the exercise description, where is it? Not that. Yeah, here. We don't know any of that. Ace. We don't know if A or B or M or N. We don't know any of
no,
that.
but I think but right, but I think that that's what distinguishes between 1 and 6, though, is whether because like
Ah, okay.
because I think that it like implies that there is no relative prime between m and n, and then if they're not commutative, they are relatively prime. That's just my because it does because number two goes on
Ah,
to it,
I see what you're saying. So you're saying that if they do not commute, then they may be relatively prime, and then
or
everything
they
goes to shit.
are. Again, just kind of throwing something out there.
Ah, okay. That actually
Because
okay.
they do talk about relative primality and pretty much all the other ones too. So
Yeah,
anyway,
yeah.
okay, let's finish up. But I think that's probably the key to 1 and 6.
Okay, that's actually pretty cool. I didn't notice that. Okay, so examples again of this fun fact. So we know that they are relatively prime, which means that they don't have common prime factors when you factorize them. Uh, and m is a factor of n times k. But that's the thing. That's the thing that bothers the shit out of me. How is that true? Can you have an m that is a factor of n times a k, then they are still relatively primes? That's
And now
weird.
m is relatively prime to n. So if m is a factor of k, then it can be a factor of n times k,
No, but that's the
even though it's
thing.
not a factor of n.
No, but that's the thing, Marinho, is that you know that if you factor out m and n, they won't have common primes. But m can be described in terms of n.
No, it can be described in terms of n times k.
Well, yes,
Yeah.
there is
No,
a constant there, but
no, this makes perfect sense. Yeah, because if n is so read it backwards, right? If m is a factor of k, then m is a factor of n times k.
well, of course it
It
makes
goes
sense
both
if
ways.
you read it backwards, Ace.
No,
But
no, I know, but going forward though, I think it makes just as much sense.
that is my problem because if they are relative primes, how can one be written in terms of the other?
Because you're introducing another factor, which is not relatively prime to m.
Do you have an example of that?
Um, uh, an example of that. Well, 3 and 2 are relatively prime to each
Yeah,
other.
Yeah.
and if k is 4,
But if k is 4, then n, which is 3 times 4, is 12, and m is definitely a factor of 12 because 12 is even and m is 2.
Ah, okay. So we have two primes that are relative. We have two numbers that are relatively prime.
and one of
No,
those
okay, okay,
numbers is
okay.
a
I see.
factor
I
of the
see.
other number. Yeah.
Okay, okay. So you essentially jump on the path of the other guy by using k.
Yes,
Sure,
exactly.
sure.
Yeah.
Okay. Thank you guys. So thanks. So yeah, so we're gonna be using that. So prove if m and n are relatively prime, then a to the power of m has order n. This is very strong. This is very freaking strong. Um, okay, so they being relatively prime means they have no common prime factors. That's what that means. So if you have a to the power of m, again, I see no relationship. Like, okay, they are relatively prime, but how does
I think
n comes into the picture of
I think
this?
the hint I think the hint says a lot.
Okay, so if this is true, and we are saying that because of this, use theorem 5 and explain why n must be a factor of k. Why n must be a factor of k.
Because it has no common factors with m.
Well, okay, but I don't see how that explains. First of all, why are we why are we interested on a to the power of mk? Because we just discovered that. Well, I was about to say bullshit. M can be written like n can be simplified into terms of k and more other stuff, right? Because m is a factor of k. We know that. Um, but
Well,
there's
actually,
more
that k
to
and this
it.
k are not really the same k, so
Wait, which case? They are all written in the same sentence. What do you
No,
mean?
no, yeah. The n must be a factor of k, not m.
Yeah, I said yeah. What did I say? I meant m. M of map.
Mhm.
Okay, so why are we starting from this point? That's my first question.
wow. This is about the relationship between art of A and art of A to some K, right? This section, this whole section.
Yeah, no, but again, if m can be simplified into k, but
No,
more
no, you're not
stuff.
simplifying. You're
Well, you
actually
are
multiplying
simplifying
it.
because you are like agglutinating everything into the k. Because it's multiple anyway, doesn't matter. Like when you say that m is a factor of k, what do you understand from that? In the example of the 12 and the true is because you have trues in the 12, right?
Oh, wait. But I think the issue is that that's only true in that sentence. If because it says if m and n are relatively prime and m is a factor of nk, then m is a factor of k. But if you go to what we're trying to prove, it's saying that n is a factor of k.
Yeah, it's another scope lemmas. The symbols are the same, but the value, the
Yep,
bindings
Ah,
different
are
scope.
different.
Yeah.
okay. The scope is fucked. Okay. Okay. So how do you guys start this one? Ah, it's already late. I have to go. How would you guys even start this one? That's the question.
Uh, well, we're basically saying, okay, I have two numbers. They are relatively prime to each other.
Man, but if the scope is not the same, how can you like where is the n coming from? This is
It's
so fucked
coming
up.
from it's coming from earlier in this point one.
Oh, when you said scope, you mean the scope of this and the scope of this.
Yes.
Yes.
Ah, okay. I understood that you guys were saying that this is a scope that is different than this one, but
No.
that's not the case. I see. Go, Mari.
Well, you're starting with a to the m, and you want to figure out what's the order of that, right? Um, well, clearly, if you do a to the m to something else, to some k, and that's equal to identity, then the order of a to the m needs to be a divisor of k, right? We know that because of how
That's
of
pretty
how
strong.
if we
Go on.
oh actually Yeah, because like k could be a multiple of the order, right? It
It
could
could
not be
be.
the order itself.
You don't know
Uh,
anything about the order. That's kind of the thing to me. This is just an equality. You don't know if this is the least amount.
oh, yes, yes, this is an equality. Um, but um, we know that M and N are relatively prime, which
Yes.
means that you cannot get N out of this M factor. You can only get it from K, right?
Yes.
Um,
I agree on that.
uh, and then, well, we would have to go and reread Theorem 5 as the hint tells us to, but
Theorem 5 is about the multiple. It's about the t. I remember. Yeah, this one. It's about the t. We want to say that if t, no, if this is true, if and only if t is a multiple of that. Like 100% this has something to do that we need to divide this motherflipper. We need to divide this. And then somehow the n is going to appear.
yeah, I'm going to wave my hand and say that that's it.
Dev. You know what? You do the work. You know what?
Well, I mean,
Go on, Ace.
Go, no,
Or
Tevo.
Tevo, actually.
Tevo wants to go.
I had something in mind, but I'm not sure exactly how to express it.
That's tough.
Okay,
Ah. Okay, you can cook, Tevo. You can cook. Let's wrap this up. I have to go. Anyway, so the entire thing is about more relationship between the relatively prime and and the order relationships, right? So it's also talking about proof that if a to the power of m has other n, essentially the other way around, right? Then they are relatively prime, which again is crazy. It's crazy to me that they have such an what seems to be a random relationship. But it seems to be the case that, oh, if this has ordered that, then they are relatively primes. And then the hint is assume that they have a common factor, then you can rewrite them in this way and explain that and proceed from there.
I think I know how to say what I saw. On exercise 1, uh, the order of m of a to the m is a number k such that a to the m k times is the identity, right?
Yes.
That is how you get AMK is E.
Yes.
Uh, we know from Theorem 5 that
That if this is a multiple of the. Well, if this is true, then this is a multiple of the order. That's what
well,
we
we
know.
know for Theorem 5 that n must be no, sorry. I think I have to write this down because I keep
Yeah.
forgetting what I want to say.
Yeah. No, that sounds tough. And
If
then
we don't
again,
get this today, I'll post a message in the chat
yeah.
later.
Thank you very much, Div. And then we also have that a to the power of n to the power of t equals to e. Then n is a factor of mt. Thus, mt is a common multiple of m and n. Then n is a factor of mt. Well, I mean, assuming that a to the power of n is equal to e, yeah, sure. Conclude that that use parts 3 and 4 to prove that the order of a to the power of m is that. I think this is what Tevo said before. Like all the way back to the exercise of the what was it called?
I think we skipped a line. A has order n. That's important.
Ah, okay, so that is how the n gets into the mix. Is because you know that this is a multiple of n. Ah, okay. That makes sense. Okay. Thank you, buddy. We don't know how to read, man. It's hard. Damn.
I think we just got sidetracked on the relative primality thing and we didn't read this line afterwards
Yeah,
because it's
no, but
very
yeah,
small.
no. This is huge because then you can just apply. There is like a strong relationship between m, k, and n now because you can just write. Um, Again, this is a multiple of n. You know that for sure. And this is what Tevo said, right? That if the order of well, you're definitely gonna exploit this fact that
Uh,
n in
The
k
least
doesn't.
common multiple between m and n, if they are relatively prime, is mn.
Yes, that
Just
is true.
orders n.
That is true. I know, but I think if you just do a little bit of a massage on this, now that we can just say that this is a multiple of n, I think you're gonna solve this. Which again, it's very wild that there is a relationship this intimate between the order of something and the exponent. That's weird. It's very weird. And then finally, h, relationship between the order of a and the order of any k root of a. Okay, reading this time, right? So let a denote an element of the group G. Let a have order 12, and then yeah, and then we're gonna essentially do the cube root. So that say that a is equal to b cube of b for some b that is also in the group. Then b greater than something which is not in the PDF for whatever reason has order 36. And yeah, and then show that this is true. This seems very obvious, right? Because we know that a to the power of 12 is equal to identity, well, to identity element, and we know that each a is b to the power of 3. But then you have a 3 on the inside and then a 12 on the outside. So you're gonna get this. Then show that for each factor k of 36, b to the power of k is impossible. Example: if b to the power of 12 is equal to e, then you can write it like this, and then this is gonna be screwed. Is that clear? Okay, okay. I don't know if this is clear. To me, this is very clear because you know for a fact that this cannot be true, right?
Because we're assuming that A has order 12 from the
Yeah,
very beginning of
yeah.
this
We're not
exercise.
assuming. We know that. Like this is stated on the problem. It's definitely 12. Then if this was true, then this is wrong. But this cannot be wrong. So this must be wrong. And this is always true. This is always going to be wrong if we use a factor of 36.
Yeah, proof by contradiction like earlier.
Yeah. So like that's like I'm dumb and I could do that. Like that's what I'm saying. Um, and then it's essentially a bunch of that. A bunch of that, 2 and 3. Explaining why the order of b is a factor of nk. My understanding of this exercise is that it is a bunch of that. It's a bunch of replacing things by other things that are like already with an exponent that is different than 1. And you keep doing that, and then you're gonna like, and then it comes again the relatively prime thing. Um, what the heck is the comma doing here? What is the meaning of that? Does anybody know? I didn't notice that when I was reading that. Is that correct in the print?
I think that's supposed to be a prime, like a tick above the n, right? N prime
Oh,
times
it's
k.
definitely above. The printing, man. Like the PDF. What the fuck? Uh, yeah. But again, my understanding of this exercise is it is a bunch of manipulations using the root thing to make even more relationships with the order, right? And then apparently there is a relationship even like a relatively prime relationship even on that level. Um, wild, wild stuff.
Yeah, number theory can go very deep.
Um, let A have order n. Let k be an integer such that every prime factor of k is a factor of n. Prove if A has a k root b, then the order of that b is going to be n to the power of k.
I think this is just basically the generalization of everything you've done before, right?
No, but this is still very strong, isn't it? Because you're saying that you have an integer k. Every prime factor of that whatever integer is a factor of n, which is the order of a. Then you have a root on the kth, then somehow the root of the individual. Like having a root means a is equal to the b to the power of k, right? And then the order of the individual b is equal to n to the power of k. You probably have to write this down. But again, I'm still having trouble with the whole fact of like this part.
I mean, if you go back to the first one in this section, you had an A where the order is 12, right?
Yeah.
And then you say that, okay, A has a cube root, so there's some B where if you cube it, you get A, right?
What is the order of b in this exercise?
Well, in this case, well, B is the root that we're talking about, right?
Yeah.
And then K is the order of B, which in this case is 3. And 3
Yes.
happens to be, well, it's a prime number, so it
Oh,
only has itself as a factor. And it is a factor of 12, importantly.
no. This example follows the conclusion of 6, right? Because this is essentially saying the order of b is equal to 36. My problem
Yeah.
is that we have to derive the generalization of that by this part. Because in the example it's pretty simple, right? Because k is 3, and that's definitely a prime factor of 12. So that's fine. But it's saying every prime factor. So if k was like 18, then the 3 and the 2 must be there, right?
They would be because, well, they are both factors of 12 as well.
Every no. But every prime factor of k. So this is we are only caring about the 3. What are the prime factors of 3? Only 3.
No. In this case, if you gave the example of 18, right?
No, 18 being the n, right? Well, it doesn't matter. If 18 is the k, then you need to grab the prime factor, every prime factor of 18, right? Which is 3 and 2.
Yeah.
Then that must appear in n as a
Yeah.
factor. And then from that, I'm having trouble doing this jump of like, this to me is pretty obvious, but this, even though it's a generalization of that, it's not as obvious to me. What if what if this was a to the power of b to the fifth? Like b to the power of 5. What would be the order of b? It would be 60, right?
Uh, well, not necessarily. It could be less than 60.
Well, you could. What would that be then?
Uh,
I think it
I mean,
must
it
be
could be.
60 because of this proof.
I mean, it could be 30.
It could be 30. Really? With A having 12 and this being 5?
I mean, if the order of b is 30, then b to the 60 is also identity, right?
No, 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 but you're going from the assumption that it is 30, right? I'm not going with that. I'm asking the question. If the order of A is 12 and this is A equals to the B equals to B to the power of 5, what is the order of
Well,
B?
well,
My understanding is
that's
that it must be 60 because of this proof. If you do the same thing, right? If you, especially the second part, aren't you gonna also reach the same contradictions that we did before?
would you? You would have to do all of the. You have to prove that all of the products up to b to the 59 um, cannot be identity.
No, I don't,
I.
because that's the thing.
You
We
do.
only use divisors of that. Again, you need to show that for each factor k of 36, right? So in my case, I'm saying this must be 60. So if you do k like 1, 2, 3, 4, 5, 6, 12, 15, 20, 30, if you do all of that, you're always going to reach this contradiction.
Will you actually?
Well, that's what my understanding is. I'm going to say it like that. That's what my understanding is. Um, but maybe I'm wrong on that. Especially because I picked an example that the relationship between the 12 and the 5 is kind of like non-existent, because there is a relationship between 3 and 12, right? Which again is kind of the point that this is trying to make, that every prime factor of k is a factor of n. So I'm trying to not do that to see what happens.
Well, we would have to try to do this proof. I'm guessing, and I don't know if that's actually the case, but I'm guessing uh, there will be a case where, yeah, actually this could be identity.
Wait, which case? The one down there, or the example that I
The
just
one
said?
with a equals b to the 5,
And A has order 12.
and a has order 12, yeah.
That's tough. That's pretty tough. I don't know how you're gonna conclude what you said. That still seems to me like hand wavy, because there will be no factors, right? That's kind of the thing. In my example, there will be no factors because this worked because 12 is a factor of 36, and you can write b to the 12 in terms of b to the third. But I'm proposing doing b to the 5, and I'm saying that the answer is 60. So I'm saying b to the 60 is equal to e, and for each factor k of 60, this should be impossible. But that's the thing. Not all factors of 60 can be written in terms of fives. So maybe that is why this needs to be true. Huh. Because if this is true, you can always factor it, right? When you're doing this step of the proof here.
Yeah.
If this is true, then you can always do that up there. I'm satisfied with that. I don't know about everyone else, but I'm satisfied with that, reaching that. I'm good enough. Anyway, so next time, which by the way will only happen like 2 weeks from now, like I'm very sorry about that. We're gonna talk about chapter 11. I'm gonna finish the recording now.